And so we talked in this class about how we can use finite element methods to solve problems where we have second order derivatives in space, such as the Laplace equation for flow or diffusive transport, and also it's actually the same equation for solid mechanics as well. We've talked about the time derivatives, which is zeroth order in space, which allows us to be able to march in time. And we've talked about the advective or convective term in, for instance, the advection diffusion equation, which is a first order derivative in space. And it turns out that that first order derivative in space is actually not so easy to deal with. And so having initiated this by going to that page, I'll search back for the page I wanted to find in the first place when we were talking about transport. And it would be somewhere right here. Okay. And so, yeah, this might be worthwhile doing. So we talked about solving the advection diffusion equation, where the advective term is this particular part, which is here. No, sorry. This part here. And it's the term that we always refer to as a velocity times dc dx. And so when we work on this, the Eulerian method to do this, we end up with a matrix relationship, which in this component here is this term. It's actually the same form as the coupling equations in the BO poroelasticity for the fluid that's squeezed out by strains and the body force which is applied by the fluid pressures through Terzaghi law, interestingly enough, because they're both first order derivative terms. But it has the shape functions, the derivatives of shape functions, and a velocity applied to it. And if you remember this, I think this is stuff that you did online yourself, is that if we look at this advective equation, it has some interesting components in it. The first is that no longer is it symmetric, like the diffusion equation is, symmetric around the leading diagonal. It's anti-symmetric, if you like. And it's no longer positive definite because it has terms on the leading diagonal which can be negative, which are partly ameliorated because when we want to get the combined relationship for diffusion and advection added together, then we add these two terms together. This term here and this term here. And so long as the value of the velocity is pretty small, this term here is quite small, and it doesn't make this value on the leading diagonal negative. But if it's large, then it has the possibility to do that. And that's the source in the mathematical sense, I guess, of the instability. The other physical exposition of this is that you can do a very simple example using two elements here, as we tried to do in this class, for flow down a two-element geometry of 3 nodes where we define the velocity. If we keep the concentration at the upstream edge constant as an input value and downstream as constant as 0, it's kind of an artificial condition because it doesn't really allow it to ultimately get to the case where it would be a constant concentration all the way through here, as you'd expect with plug flow, right? If you started pouring dye in here and allowed it to go down here, then ultimately the concentration here you'd expect would equal the concentration at the input for plug flow. But if you artificially hold this at 0, then it can never attain that. I suppose the physical interpretation for that would be if you had flow down here, but if you had water going across here at some high velocity, that would basically make that concentration 0. Or a large reservoir, I guess, would be the same thing. A large reservoir and complete mixing would give you that concentration equal to 0 all the time. But anyway, if you add these expressions together for a defined 0 condition here, a defined unit concentration here, where the only unknown is at this point here, you end up having only one equation to solve for, the central equation. And if you go through everything that we've done in this class to figure that out, to find out what the concentration is at the central node, you end up with a recurrence relationship like this. And it tells you that between the upstream node and the downstream node, the magnitude, if the velocity is 0, then it's just equal to a half, which is the diffusive solution. It'd be the same as Darcy's law if it was a flow problem between upstream and downstream pressures. And if the velocity is positive in the downstream direction, in other words, is positive by definition, same direction as the positive x direction, then the concentration upstream would be larger than this diffusive only value. And if the flow was in the opposite direction, in other words, velocity is negative, then the concentration would be less. And so that would be what's expected. But of course, from this equation, you can get these values which don't make any sense when this, for instance, can actually, if you have a large enough velocity, if you have a velocity of 10 here, for instance, and a diffusion coefficient of 1, then it would be, well, actually, if you have a velocity of 40, then it would be 40 over 4, which would be 10, and this would be 10.5. And so the intermediate concentration, instead of being 1, would be somewhere up off the top of this page, which is unrealistic. And so the limiting value where this solution will start to not make sense is when this value of C2 is greater than 1. And so in other words, the limiting value of velocity term, if this is actually greater than a half, you get unrealistic solutions which make no sense. And of course, those could be physically real situations, but numerically, we won't get a result that makes any physical sense. If this is very high velocity, you'd expect it purely and simply to be plug flow that goes down here and would look something like this, I suppose, if you're washing out this node. And so to be able to get around that, we have to be able to do something to take care of that. And so Eulerian Lagrangian methods are one way to be able to do that. So let's go back to that, but we can refine that. And so that's our basic problem we're attempting to solve. Oh, found it straight away. That's pretty good. And so this is one way to be able to do this. And actually it's pretty straightforward. If I make this and close this. So the basic idea is this, very straightforward. So Eulerian, Lagrangian, methods. Or vice versa. You can switch those around. There's also a technique which I don't think we'll talk about, which is also referred to as arbitrary, ALE. Lagrangian. Eulerian methods. So A, often truncated as ALE. You'll see if you look on Google, you'll find ALE, which is not beer in this particular case. And so the idea is relatively straightforward. We've not really talked about it before, but if you think about Eulerian methods, then you can imagine, say, solving maybe a deformation problem where we take a mesh and we apply a load on it to deform it. And we've made this comment before about how this would deform if it was a deck of cards into some new geometry. And we could actually attempt to follow that geometry, or we could attempt to allow things to move through it. And so the Eulerian way of solving this would be to take this geometry, which is this, and we'd hold the mesh constant, and we'd calculate some deformations from the mesh maybe moving through it. and not really accommodate the fact that the mesh is moving through it. The Lagrangian way would be to take the mesh and allow that mesh to deform with the deformations that are occurring. So it keeps within the mesh the same mass within each element as those elements individually deform. And so you can certainly apply it for deformation problems. It's probably more appropriate to think about it for flow problems, right? In terms of a flow problem, then physically we have a mesh, and that physical mesh might be something that we try and apply a pressure gradient across over some length, and we get flow through here. And we know that we don't modify this mesh in any way. We merely do some kind of accounting for each of the elements that we have in here, that some amount of stuff comes in from one side, some amount of stuff goes out the other side, and we do this accounting of this amount on this static element. It's an Eulerian element. It doesn't move, but stuff is moving through it, which we don't really particularly follow. If we were going to follow that using a Lagrangian method, then what we would do is we put an element around it that would track with this location at time t0, and maybe then at time t1, the element might look like this, because it's merely tracking that amount of mass as it goes through it. And then at time 2, then maybe it would look like this, because it's attempting to keep in it. So this is Lagrangian and Eulerian. And so we actually encompass this with the same membrane that surrounds the amount of fluid that's physically moving through it. And so the reason for mentioning this is that Eulerian methods, if you apply to solve things like dCdx on these first order derivatives, then Eulerian methods work really poorly on this. But Lagrangian methods have really no limitation, because you're just encompassing yourself around a particle, and you could calculate the new location of that particle as its location at some updated time is its previous location at time t plus the velocity it travels at multiplied by a time step. And so these would just be vectors. This would be t plus delta t. Delta t. Let me just get rid of that. And so you can imagine if this x-coordinate was the center of this mass, then at these three successive time spots given by these three different colors, this would be the x-coordinate of that particular mass. And you could follow it through here. And so Lagrangian methods are quite good at taking account of this behavior. And so when we have systems that involve this expression here, we can solve part of it in this Lagrangian space frame, and then the other part in this Eulerian space frame. So I tried to work a little example to be able to demonstrate this today. So let's see if we can do that. That'll be my interactive activity for today. And so, but the basic idea is quite straightforward. And so the idea is basically this: is that if, for instance, we take the advection diffusion dispersion equation, the AD equation, we've written it typically as something which is something like rate of change of concentration with time is equal to some diffusion coefficient times second order partial with respect to space minus the advective velocity times this concentration gradient, dCdx. And this is the term that we don't like to deal with. So let's, instead of concentration, just because it's in the one reference that we use, let's write concentration as a mass. And so we'll just replace it and write it in this form. And I'm going to move this term that's on the right-hand side to the left-hand side as v dc dx equals diffusion coefficient. So follow my own rules. So we have this. So we haven't changed anything. But what we can do is we can look at this as a derivative, and we can write it in terms of, not to confuse us, a substantial derivative, which is dm dt. And dm dt is just saying that we can take the derivative of mass with respect to time, and we take that derivative of mass with respect to time. So humor me in this, I'm not adding 4 of these together. And what we can do is we could multiply each of these by the other 4 components of our universe. So the 4 components of our universe are that we live in a 3-dimensional world, x, y, z, and things change with time. And so we could multiply this first one by 1, which is this. We could multiply the second one by something related to, again, the x-coordinate, but 1. Something related to y, which is 1. And something related to z. And so if we look at these, all we've done is we've expanded this. We've written this as a sum of individual components. And the reason that we don't get 4 dm dt, this is not equal to 4 times dm dt, because each of these are orthogonal to each other, right? X, y, and z are all orthogonal to each other. So the component of anything in the x direction has no influence on anything in the y or the z direction, and they also exist at different times, and so they're separate from each other. And so these are actually, I didn't need to do that. These are actually just individual components. And of course, these individual parts here, this is just the velocity in the x direction, this is just the velocity in the y direction, and this is just the velocity in the z direction. And this, of course, is just 1. And so the substantial derivative is just equal to dm dt plus velocity in the x direction, dm dx, plus velocity in the y direction, dm dy. And I guess since I don't do it, but just for completeness. And so the reason for doing that is that you'll notice that this part here is exactly this substantial derivative. And so we could write this as being this dm dt. And so the way of this refers to just the fact that there are different reference frames. And so in other words, the reference frame that's attached to here is this is the change of mass that you'd see if you were physically attached to it. And this is the change of mass that you'd see not only as changing with time, but also as maybe it moved past you and moved away from you. And so this is represented to a static reference frame where you're viewing something that is moving relative to you. And this is the reference frame where you're actually attached to the thing that's moving. Say, water moving up in an elevator. You're actually in the elevator for this. For this, you're standing on floor 5 as you're watching the elevator go up past you and seeing how the velocity of the elevator goes past you. If it's in the x direction, if x is up, and how the mass changes as it goes from one location to the other. You get exactly the same results by looking at it, but you're just viewing it from different reference frames. And so the reason for doing this is that now what we can do is we can write our advection dispersion equation as this, which is just change in mass with time is equal to a diffusion coefficient. So I guess we probably should give it some little attachment to it so that we can make the distinction that this isn't the derivative, but this is diffusion coefficient, and how that changes with location. So you'll notice, of course, that now this term, which is our problem child, is no longer present on its own, but it's embedded in this term, which is a first order derivative with respect to time, but not really with space. It kind of embodies, this is embedded in it, but it doesn't explicitly represent that. And so this, while this was the advection dispersion equation, because it had advection in it, this is just a diffusion equation. And so the idea is is that we solve this part using a Lagrangian method. And we do the other part by using an Eulerian method, which all sounds very grand, but it's really quite straightforward. And so the idea is, let's go to some of the printed stuff that we have. I'm thinking here. So this is it written out, and probably it's best to look at a figure first that physically explains what's going on. It's really very straightforward. And the idea is this. So you take your grid, that would be your, say, your finite element mesh, and instead of solving it in the way that we've talked about in terms of defining boundary conditions and defining the equations for flow in the Eulerian method that we've used so far, we've only used the Eulerian methods. Instead, what we do is we take particles that represent some amount of mass of the contaminant that's present in the system for the flow problem. And we have this mass that's present at this location. We know that in one Lagrangian time step, the location of that will change as being equal to x0 plus delta x, which is the same as x0 plus the velocity times the time step. And we take this particle and we physically move it over one time step to a new location. Once we have it in this new location, it may have crossed from one particle, one element to another, but now we can actually interpolate this and use it to distribute it back at the individual nodes, which is how we do our solution in the Eulerian part. So this would be the Lagrangian step. So it puts it in a new location. And then the Eulerian step is to take this mass here and figure out exactly what its interpolated magnitudes would be at the individual elements. And those individual magnitudes at the elements, you could think about it by just using the same shape functions that we've already used before to distribute it from the nodes to any particular point in the system. So in other words, in our past life, what we've done is we've had nodes, values of concentration at nodes 1, 2, 3, and 4. If we use the shape functions, we can get the concentration at any location as equal to the product of the shape functions times the nodal values of concentrations, right? We've used this many times. So in other words, we could calculate what this is as a function of known values of this and certainly known shape functions. Our interest here is to do the opposite. We start off with this, and we'd like to figure out exactly what these magnitudes are. And so to do that, all we need to do is, if you imagine taking a cross-section through this point here for maybe a 1D element, and then for that 1D element, we would have shape functions that would look like this and this, right? This would be B1, and this would be B2. This would be node 1 and node 2. Then the magnitudes of the concentration, so if indeed our mass was present at this point here, and we draw that down through here, whatever those would be, then what we could do is we could calculate the fact that the mass applied at element number 1 is equal to the value of B1 multiplied by the mass, whatever this is. And the amount of mass at 2 would be equal to the shape function B2 multiplied by the same mass. And so in this particular example, the mass at B1 would be something like, it would be, let me change colors so you can see it. So in other words, the value of B1 is this amount here, which is something less than a half, which is, say, 0.4 times m. And the amount of B2 would be this amount here, going through this point here, would be, by exclusion, it would be the opposite, it would be 1 minus that value of this. And so if we know what the mass is at this particular location, then we can put a portion of it at each of these nodes. You see that the sum of these, if you add them together, is equal to 1 times m. So it's conserved the amount of mass. And it has now distributed appropriately at these nodes. And now, once it's at these nodes, what we could do is we could allow diffusion to occur. So in other words, we've calculated an amount according to this equation, which is the Lagrangian step. We have a second part that we need to deal with, which is the diffusion coefficient and the mass redistribution because of this fixed law part. And so what we would do is that now we can use these concentrations calculated at these nodes to now redistribute it throughout the rest of the mesh just by solving the diffusion equation for one time step and see how it will change. That redistributes those masses. We then go back and we start with the particles again, and we make another Lagrangian step. And so that's really what it is. So that's the physical workings of it. If you want to look at how you write that mathematically, then this is also, I guess, a reasonably succinct version of that. And so this is exactly what we've talked about. This is our advection dispersion equation. We've called this maybe D star, just to distinguish it from the fact that we'll use this substantial derivative. This part here is what we've called dm dt, which we've just rearranged. And so since this is just a first order in time and zeroth order in space, then when we write our system of equations to describe this, the finite element system of equations for this would be something like S m dot plus k m equals q. This would be our finite element relationship. The advection term is embedded, if you like, in the S matrix, but the S matrix would be no different from this integral B transpose B dV term that would exist here. This would be our normal conductance matrix, which would be A transpose dA dV. I guess this should be D star maybe if we're talking about those. And so it's written out in a slightly different way here, but you see exactly what the portions are. This is using n for the shape functions, which is quite often used. So this is derivative of the shape function. So this is A, this is the diffusion term, and this is A transposed. So this is the K matrix, if you like, that we have here, multiplied by M. This is the S matrix, or storage matrix, that we have here, multiplied by M, and also the time derivative. M dot is just this. And this is the flux on the boundary. Which we've not used in our other portions. And so what we could do is we could solve this matrix equation in exactly the same way that we do it for the flow, for the diffusion only problems, and it would look something like this term down here. So in our parlance, this would be 1 over the time step multiplied by the storage matrix plus the conductance matrix, operating on nodal values of mass, which is this term here. This is at t plus delta t. And this is equal to a term on the right-hand side, which you'll have seen before. It would be something like, I'm running out of space, so I'm going to do it down here. It would be the load vector plus 1 over time times the storage matrix. See, this is storage matrix divided by time and multiplied by the values of mass from the previous time step. Exactly the same way we've done it before. And so that physically allows us to be able to solve the diffusion part. So we're solving only for diffusion, and this, of course, is our normal Eulerian way of doing it. And in terms of this. And so we know exactly how to do this. So it's nothing any different from what we've done before. And it's all predicated around the fact that we can take this advective term and we can embed it in a substantial derivative, which then only doesn't have these unstable components in it. But it really doesn't allow us to do the advective term. So the advective part we take care of in a Lagrangian step, which is this. And it's really just to calculate what the new value of the mass is as a function of its new location. So in other words, we can calculate a new location. So in other words, if we have x and y, then we know if the mass exists here at some time, and if the velocities are a velocity in the x direction and a velocity in the y direction, then the trajectory of that mass will move by some amount, and that amount will be delta x and delta y. And merely delta x will equal the velocity in the x direction times the time step, and the change in y is going to be the velocity in y times the time step. And that's exactly what this term is here. And this is just x0. Where we use x as a vector of x, y, and z for 3 dimensions, or x and y in 2 dimensions. And so that's all it is. And so it's really pretty straightforward method. It just relies on 2 steps. And so I thought we might do an example. I didn't quite get through it before I came to class, but I'm close enough to be able to fake it maybe. And so let's try an example, just going through it. Okay, so that's it. So the idea is that because there's no advective term, the advective term is taking care of this step, that this is unconditionally stable, and it will work its way through the system without any kinds of kinds of problems. So, oh, I didn't want to do that. I want to do this. Okay, all right. So here's my attempt at doing this. So let's try an example. So the example is, how are we going to do it? So here's the example. The example is a single element. And we'll have upstream nodes 1 and 2, or nodes 1 and 2 rather, not upstream nodes 1 and 2. It's defined relative to the x direction. And we can think about the physical behavior is that we have fluid going through here at some velocity v equals 2 meters a second. We have some length of this thing, which will just make 1 meter. We'll have a diffusion coefficient, say, that's equal to 1 meters squared per second. I think that's the right units for diffusion coefficient. This is our d star. And we'll represent it by shape functions, which will look just like the ones that we used before, which are these linear shape functions. And this would be B1 is going to be equal to 1 minus XORL, which is this. And B2, which is equal to just XORL. Satisfies all the things that we said they had to, right? It's equals 1 at the node in question, 0 at the other nodes, etc. for each of them. And so if we wanted to, we could write our shape functions out as equal to 1 minus XORL and XORL. It's a shape function term. And let's see if we can, how we can do this. So let's divide this. I don't know if it'll fit on here, but my plan is to divide this between these two different activities. The Lagrangian step and the Eulerian step. Okay. So the idea for the Lagrangian step is that we are going to take this geometry and we're going to put in a little mass of something at this point here, which is equal to our upstream boundary condition. So what we're going to do is we're going to put this boundary condition equal to a concentration of 1, and we're going to put this concentration as undefined. So this is going to be the upstream concentration that's going to be pushed downstream by flow. And what we'd like to do is, if this is a concentration of 1, we'd like to calculate the mass that we put in. And we could make a good estimate of the magnitude of this mass for a particular time step. So we're going to choose a time step of equal to 0.1 seconds. And so if we want to get the mass that flows into here in that time, it's going to be the advective velocity times the cross-sectional area of the element going in. So let's make A is equal to 1 meter squared. The concentration and the time step. So if we dissect this, this is what we call, this is volumetric flow rate, what we call Q, right? The velocity times the area is the amount of water that's going into the system per unit time. The water has some concentration, so you multiply the volumetric flow rate, which is the amount of water, times the concentration per unit volume of water. That gives you the mass rate, the mass per unit time. And if you multiply the mass per unit time by this, then that gives you an overall mass. So that's the rationale for that. And so I guess we could check that in terms of dimensions. The dimensions are meters per second. The area is meters squared. The concentration is mass per volume. And time is seconds. So you get the seconds, you get the meters cubed, and you're just left with mass. So it's the right, at least it's the right units, which I guess is a good start. So what are we going to want to do now? So we're going to start off with this value here. At step 1, we're going to calculate where that mass goes to. And so we can get the x-coordinate at time t plus delta t is equal to x-coordinate at t plus the velocity in the x direction times delta t. And so if you put numbers into this, this is 0, this is plus the velocity, which is 2 meters a second, and delta t is 0.1 of a second, so this is 0.2 meters, I guess, for that. So that's going to be the physical location of this first component, which is going to be some distance of 0.2 meters in it. And the total length is 1. And so that's our first calculation. And so what we want to do then, this will be true, I guess, this recurrence relationship will be true for all times. It'll just be updated by a value of x. And so what we can do from that is we can calculate the distribute the mass to the nodes. So we do that merely by using what we defined before as concentration is equal to shape functions times nodal concentrations. But here we're going to use mass is equal to shape functions times nodal masses. And so I guess for our particular case, this allows us to get the mass at node 1 is equal to B1 times the mass, and the mass at node 2 is going to equal to B2 times the same mass. And the easiest way to figure out exactly what that looks like is just to draw this diagram, the shape functions on it. And so we have a mass at this particular location here. And we know what the values of these shape functions are. And so this is going to be, for our first step anyway, it's going to be equal to m1 is going to be 0.8 times m, and m2 is going to be 0.2 times m. It's just these heights at this point, and you can just scale it off as to what they would be. Just from, you can calculate it from shape functions that we have here, which would give you that magnitude, but you can see it just by geometry. This has to equal 1, this is 0, And so they're similar triangles that allow you to scale between them. And so for our particular case, if we throw this in here, this is 0.2 kilograms, I guess. And so these values of M1 and M2, if I write them on the other side because I've run out of space, would be the product of 0.2 times 0.8, which is 0.16, right? And 0.2 times 0.2, which is 0.04. And so what we could do, what the easiest thing to do, is to make a table which has location defined and also the time steps. Step 1. I'll only go up to step 4, so I'll put that on as well. And so the locations are just the physical locations of those nodes, or the masses, which could be at 0, it can be at 0.2, it can be at 0.4, 0.6, 0.8, and 1.0. And I'm going to draw a line that keeps these separate at after 0 and here. So this is just between these two numbers. And what we've done is we've calculated what these initial distributed amounts are. And they are node 1, I guess it's 0.16. And at node 2, it's 0.04. And it's due to the fact that at this point here, we have a mass of 0.2, right? So that's the blob that we have, which is of mass 0.2 kilograms. It sits here, but we're just distributing its impact between the two locations, one upstream and one downstream, and we note that these values add together to equal 0.2. So mass is conserved in some way. All right. So that is the Lagrangian part. The Eulerian step is that we're solving this equation, which is dm dt, so whoops, equals d star d2m dx squared. So this is what we're solving. The finite element form of that is, as we said, is something like this storage matrix plus this conductive matrix is equal to the boundary conditions. So this is our normal finite element statement. We know what these matrices look like, right? We know that the K matrix, the storage matrix is equal to area times length times over 2 times 1, 0, 0, 1. So that you add these two terms together and look at it as a scalar, and it's just equal to the volume of the element. So by definition, that is this matrix. We know that the K matrix is equal to diffusion times area times length times 1 minus 1 minus 1, 1, which we see. And so what we could do is we could write that out in longhand for this one-dimensional system with just two nodes. And it's going to look something, well, not something like, it's going to look in terms of these terms, it's going to be AL over 2, 1, 0, 0, 1. multiplied by masses at nodes 1 and nodes 2. Actually, rates of changes of those, right? These are m dots. And it's going to be equal, add to that diffusion star, I guess this should be a star, times area divided by length, 1 minus 1 minus 1, 1. And it's going to be equal to the fluxes at those two nodes, however those are defined. Whoops, I missed out the whole term. So let me just get rid of this so I can write that again. I didn't write the masses in here, so this is mass 1 and mass 2, nodal values of the masses accumulating at the elements equal to Q1 and Q2. So those are the terms that we have. And so we know from this that if we define the concentration at this node, it's the same as defining the head at that node, or the same as defining a force at that node. In that case, this equation doesn't need to be solved. So in other words, when we solve this, we're only going to need to solve the lower portions of this. And so when we manipulate this to be able to solve this, as you'll recall, k plus 1 over the time step times storage multiplied by mass is equal to Q plus 1 over the time step times storage times the mass from the previous time step. Okay. And this is the time for the future time step, t plus delta t. Then we're only going to have to solve one equation. It's going to be a recurrence relationship. And so we can look at what these individual terms are going to be. I think we defined this is equal to 1, the length is equal to 1, the area is equal to 1 meter squared, and so this term is going to be equal to 1. This area times length are also going to be equal to 1, so these terms, I guess, would be equal to 1/2. And so if we write out this equation in longhand, it's going to be value of the K matrix. There's only one term. It's going to be 1 plus storage, which is equal to 1/2 times delta t times m. So this is 1 plus 1 over 2 delta t times the mass at node 2 at time t plus delta t. And that is going to be equal to this relationship here, which are the fluxes at node 2. It's going to be equal to the fact that we've had to take this term here for m1 times this onto the right-hand side, right? We need to keep track of this. So it's going to be, if I do this right, plus area times d over L times m1 plus this term, which is storage over delta t, which is 1 over 2 times the time step multiplied by the mass at node 2 at time t. And so that's our recurrence relationship, which allows us to solve. And so of this is going to be constant. It's not going to change with time. We chose a time step of 0.1 seconds, and so this is going to be equal to 1 plus 2 times 0.1, which is 0.2, which I guess is 5, right? Times m2 at t plus delta t. Doing okay for time. And this is going to be equal to these terms here. So what the flux is not defined is equal to 0. the mass at node 1 stays constant and is equal to 1. And so this is going to be equal to 0 for this term. Area d star and L are equal to 1, and this is equal to 1. And so this is equal to 1 here. And so this is 1. And this final term is going to be equal to 1 over 2 times delta t, which is 1 over 0.2, which is 5, times the value of the mass at location 2 at time t. And so in other words, we can always calculate the revised magnitude of this nodal mass at time t plus delta t by just dividing through by 6, which is equal to this recurrence relationship, which is going to be 0 plus 1 plus 5 times m2 from the previous time step, all divided by 6. So we're getting there, don't worry. So I've set it up this way just to remind ourselves of the fact that we're trying to do two things. We're trying to take a time step where we move a particle forward, and then we distribute that amongst the nodes, and then we can allow diffusion to occur to redistribute that amount in the next time step. Then we introduce another particle, allow the other particles to move through the system, and then get to this new place, distribute them from the inside of the element to the nodes, allow diffusion to take place once they're in the nodes, and then go back to the same repeat. And so hopefully this will start making some sense here. So we took one step before where we ended up with this particle located here, and we distributed it between the two different nodes. And so now we could take these values for both the concentration, this is, I guess this is M1, and this is M2. I suppose I should have done it in blue. And so what we could do is we only need the value for M2 to be able to do this. And so if we take M2, we could calculate for the first step. So I'm going to label this step 1. It's going to be what? M2 goes to be equal to 0 plus 1 plus 5 times M2. M2 is equal to 0.4. 5 times 0.04 is 0.2, is that right? All over 6. Is that the value I have? Yes, which is 1.2 over 6, which is 0.2. Right? Yeah, 1.2 over 6 is the same as 12 over 60, which is 0.2. And so this magnitude now is 0.2, and that would be the solution at node number. So this is the solution at time step 1 after it's diffused of a concentration or a mass of 0.2. Okay? So that's the solution. And where am I going to write that? So maybe this is 0.2. So this is the solution. So now what we're going to do? No, too early. Next time step, what we're going to do? We're going to take this and we're going to move this ball here, but we're also going to inject another ball. And so we know how far it travels in one time step. It's 0.2 of a meter. And so at the next time step, we'll have this value here will move to this new point here, and that will be its mass. And there will also be another one injected at this point here, and these others will be zeros. We can do the same calculations we did before to calculate what the mass is. And the mass at node 2 at the next time step. So this is time step number 1. This is time step number 2. So M2 is going to be equal to what? It's going to be equal to, it's going to be the mass has now moved to this point, and so it's going to be equal to B1 M first one plus, sorry, B2 times the M at the 0. I don't know what else to use, but it's going to be equal to 0.2 times 0.2 plus 0.4 times 0.2. So this is the mass, and this is its location, the weighting of the shape function. So it's 0.2 of the distance along here, and this magnitude of the weighting of the shape function is 0.2. It's 0.4 along here, and this weighting is 0.4. And if you multiply those together, I guess the recurrence relationship is going to be B, what's what I want to, it's going to be sum of B times N, which is equal to 0.2 plus 0.4 times the mass, which is equal to 0.6 times 0.2, which is 0.12, right? So the value of 0.12 ends up being this. This is our new value at this node. It's been advected there, and so it's the effect of advection, but it hasn't got diffusion included. So now we go back to the diffusion step, and we go to step 2. So the revised mass at that node is going to be equal to this recurrence relationship, 0 plus 1. So this is these terms. This term doesn't change, this term doesn't change, but this term has. And this term is going to be equal to 5 times whatever M2 was. 5 times this is 0.6, I think. Is that right? Is it 0.12 or is it 0.14? Where did I get that last time? Five times I had 0.14. What? Doesn't matter. Okay, so I'll go with what I think here. So what do we say? 5 times 0.2 is 5 times 0.012 is 0.6. Which is equal to 1.6 over 6, which is whatever that is. Does anyone have a calculator? Come on, let's be active. Well, okay, I'll do it then. Is that right? Did you do it in your head? What is it? What, 260? Okay. 0.260. And then, so basically this, whoops, don't do that. Why did I get point? So I've got my little sheet here that number, instead of being this number here, instead of being 0.12 is 0.14. But no, doesn't matter. Anyway. So 0.026, and so this is 0.026. This here is 0.26. So now the next step is we put in another particle. It goes here. We calculate the weight of those particles and what influence it has at this point. At the third time step, it's going to be equal to, again, this recurrence relationship, which is the sum of the shape factors multiplied by the mass. And so there'll be 3 particles now. So there'll be one here, which is the newest one that's been added, the one that was added at the second step, and the one that was added at the 0th step. And so this will be 0.2, 0.4, and 0.6 along here, and corresponding numbers of this curve here. So this will be 0.2 plus 0.4 plus 0.6 times 0.2, which is 1.2 times 0.2, which is the same as 0.24, is that right? So let's keep our colors constant. This is 0.24. We apply diffusion to it again in step 3, or time step 3, and that is that the mass of the node has to equal the boundary condition, which doesn't change, the effect of the flux that doesn't change, the boundary condition, which doesn't change, plus the value of 5 times 0.24, which is 1.2, I think, over 6. And 2.2 over 6 is 0.333333, is that right? And I guess that's what this is. And then we repeat, add another component. Now this is 0.2, 0.2, 0.2, 0.2. And those are now going to be at step 4. The recurrence relationship is 0.2 plus 0.4 plus 0.6 plus 0.8, all multiplied by the same mass. And 8 and 2 go together, 4 and 6 go together, so it's just 2, which is 0.4. Step 3, which is and if we go back to this, step 4, you get the idea. So just finish it off, just because I can. 0 plus 1 plus 0.4 times 5 is 2. Times 6 is a half. And this is 0.5. And we've run out of space. You'll be happy to know for another column. So what do these results mean? So basically this is telling us that if you looked at a time series for what's happening at at node 1, then it's going up linearly with time, and by the time we get to t is equal to, this is 0.1, 0.2, 0.3, 0.4, so this is 0.4, sorry, wrong axis. This is 0.4 seconds, then the value of this is equal to 0.5. Ultimately, it should go up to 1. And so is that physically likely to happen? Well, what's going to happen with this? What's going to happen is that we're going to keep on adding particles at this particular location. They're going to, so now we're at the point where we have a particle here. The next one will be one here. And so there'll be particles all the way through here, but it will still be less than 0.5, even though it's kind of reached the location where it should be. Oh, it's about to close. So what's going to happen is the particles are going to keep on going past this node. Because it's going out into the material beyond it, in reality, we'd have another element next door to it. And so at location 1.2, and then 1.4, 1.6, 1.8, etc., you would have those components downstream of it. And so the fact that it's reached half of its concentration as it's just reached there is that as it goes downstream, then the shape function, if you like, for the other elements that's added on here, will do exactly the same to add to its influence here. And so what we'll find is that as you go downstream, the magnitude of this concentration will actually rise to 1, which is exactly what you expect it to be if it's coming from an upstream boundary condition of 1 and being washed downstream as plug flow. It's going to end up giving the same concentration at the node that it hits downstream. And we can argue whether it's going to be delayed. It's going to be delayed by reaching that by twice the magnitude, right? Because it's going to have to work its way through to the end of the second element before it ends up doing this. Okay. I've lost it, but I haven't lost it. Here it is. But I'm about to going to lose our recording. So by the time we get to step maybe 9 or 10, when the pulses walked all the way through the second element, then the value of the concentration at this particular location is going to be equal to 1, which is what it should be. And so the method is entirely stable because it's given us a result that we've monotonically marched through to the solution, but it's going to give a diffuse front, which instead of what the front should look like, I think, is that at 0.5 seconds, if it's moving at 2 meters a second and it has to go 1 meter, at 0.5 seconds, the concentration should actually be here. So the progress should be this, 0, 0, 0, 0, 0, 0, 0, and then bang, it breaks through, and then it's constant at that magnitude. In our particular case, what it's going to do is this. But it is going to stop at this value here because it can't go past it. It's just that it's not going to get there at the right time. So it's diffused, if you like, the front that's moving through it. Instead of moving as a plug flow front, it's moving as an inclined plug flow that gives you an immediate concentration downstream that ultimately builds to the final concentration. And so if you looked at the physical representation of what that plug flow would look like, not in time, but in space, concentration, instead of looking like this, it's actually looking like this, right? It's got this diffuse front in front. It's actually closer to a straight line, right, in doing that. And so we get numerical stability at the expense of numerical, what we refer to as numerical diffusion.